Gentlemen, welcome back. Today is the day. Previously we discussed how to get started on a relay, how to figure out what elements we need to test. We have previously determined on this SEL 751 on my bench, I need to test 50P, 50N, 50Q, and 50G. What does all that mean? Well, those are the instantaneous overcurrent elements that are enabled in this relay and go to the trip equation. So how do we get started? We've got our test plan that we started last episode, and we're just gonna continue on with that. Again, I will try to make this agnostic of protection suite so that if you're following along with a different piece of software, all you'll have to do is figure out what that equates to in a different macro on a different software. All of the math works out basically the same way. Okay, so we've determined which elements that we actually need to test. We've determined which ones are enabled in this settings file, in this relay, and we know every protection element that's enabled and goes to an output. We have to test those. So number one, what do these things mean? So 50P1, 50P2, 50N1, 50G1, 50Q1, right? So what are all of those? Well, 50 is all of our instantaneous overcurrent elements. It's the ANSI device code for an instantaneous overcurrent relay. You'll see that millions of places. It's not just SEL relays. There's lots of other types of ANSI 50 devices, instantaneous overcurrent elements. The P here in SEL logic parlance means that this is a maximum phase overcurrent. So 50P is on the phase. So whatever the highest phase is will trigger the 50P element. 50N in this case is neutral overcurrent. Here's a difference between SEL and GE. On the SEL relays, if we look at the back of the relay, I'm not going to pick it up and do the whole rigmarole, but on the back of the SEL relay, there is an IN channel. That is a neutral CT channel. It is a separate physical analog input on the back of the relay that measures neutral current. That's what that's for. So I have A, B, and C phase that can each trigger 50P something, the pickup or the trip for it. I have 50N, which is the neutral, which is a separate channel. Now on GE relays, they get N and G backwards. Sometimes on some relays, it's really kind of annoying. They would call it a ground CT, and then the neutral is a calculated neutral current. In this case, 50N on an SEL relay is a neutral current channel. It's for a neutral CT. It's just the way they call it. Residual overcurrent, they call that 50G. That's our ground current, zero sequence current. That is your residual current is what they call it. So 50G, we think about that as ground current that is a calculated zero sequence current. It is the unbalance between the phases. It's a calculated zero sequence based on the other current that we're already pushing into the relay. Separate from the neutral. I know those phrases kind of get used interchangeably and they're used differently in other relays and it's horrible and I hate it. However, in SEL parlance, 50G is a calculated imbalance between the phases. It is the difference between A and B or A and C or C and A, or a zero sequence fault current. Just want you to be aware of that. We'll get into how to actually test that here in a second. Now lastly, 50Q, what does that mean? Well, that is our negative sequence current. I'm not going to teach you the math on why that's important or how to set negative sequence overcurrent protection. That's an important thing for application engineers and settings engineers to figure out and to know. We don't necessarily care about that. I'm going to show you how to test it because it's going to save us a bunch of time. So we're going to skip all the nonsense and I'll just show you how I test that on these relays. All right, so we've got 50P, 50P1, 50P2. Why do I have two of those? Well, I can set these to have two different pickup amounts, two different amounts of current, two different current magnitudes. and different delays. And so instead of setting a 51 element, it would be a time overcurrent element. If I only need 2 steps along that curve, I can do that with multiple 50p elements, multiple phase time overcurrent elements. And you'll see I can have up to 4 on the 751A. Similarly, I can have multiple steps of all of the other ones, right? So I could have multiple neutral overcurrent, multiple ground overcurrent, and multiple negative sequence overcurrent elements kind of stacked on top of each other. Additionally, they can use some of these as like a load pickup logic, that sort of thing. It can just basically be used to record any amount of current or do any amount of logic with some current. These don't have to necessarily be protection elements, but sometimes you'll see these used logically in automation systems and things like that. So they'll use a level 3 or a level 4 pickup for some sort of like load shedding logic, for example. In our case, all of these elements that are enabled go to the trip equation. And you'll see that pretty frequently. We'll have a higher amount of current and a lower amount of current with a longer delay. It's pretty common. So how do we actually go about testing? Sorry, before we jump into how we actually test these, we got to talk about the word bits for a second, how they're actually described in SEL. So 50p1t is what happens when both the pickup and the delay are satisfied. So have we exceeded the pickup for this amount of time? Well, 50p1, the pickup element, the pickup word bit, will go high immediately whenever we exceed this maximum phase overcurrent pickup. In this case, I have a 50p2p, 6 amps. So when it picks up 50p2, so it would just look like 50p2, I'll probably put it on the screen here. 50p2 picks up immediately upon current in the system exceeding 6 amps on the highest phase. 50p2t only picks up once we've exceeded that amount for the delay time. So we need to have both of those in order for 50p2t to go high. We can pick through that here in a second with some examples. So we know what 50p1t is. It is 8 amps with no delay. 50p2p, which is our instantaneous overcurrent level 2 pickup, is 6 amps, and I have a delay of 1 second, right? We determined that from our settings here. What comes next? What tests do I actually need to perform? So we're going to go back to the NETA acceptance testing standard book, right? So if we find 50 instantaneous overcurrent relay, it says I need to determine the pickup, determine the dropout. Now, we'll talk about that here in a second, and determine the element time delay. That's kind of vague. They give you a lot of wiggle room on how you actually need to test that. Can I look at an LED pickup? Do I have to record that as a contact closing? Do I have to record that as a trip to the breaker? No, you can do it basically however you want to, as long as you can make the argument that I did determine the pickup with an adequate amount of accuracy to prove that it's within tolerance for per the manufacturer. We have to infer a little bit based on how the relay works, how we want to do that. The only other considerations here, so obviously the 2 tests that we're going to do for our 50p1t and our 50p2t, 50p1 doesn't have a delay in this case, so I'm only going to test the pickup. But it operates on all 3 phases, so I'm going to do a pickup test on A, B, and C. 50p2, I'm going to do the same thing, element pickup on A, B, and C, but I'm also going to do a delay test. That is a thing that I also have to do. And what are we testing these to? What spec, what standard? Fortunately for us, the SEL 751 manual tells us how accurate these need to be per the manufacturer. So I need to prove that this relay with these settings is going to operate within the published tolerance of the manual. In this case, our pickup setting is this equation, right? So plus minus 3% of setting plus 0.02% of INOM. For most intents and purposes, it's going to be vastly more accurate than that, especially SEL relays, they're very good. It's going to be vastly more accurate than that, so I'm not going to worry about making like a custom tolerance equation in Protection Suite. We can do that, and I'm sure we'll cover it at some point in this series, but for what we're doing right now, I'm just going to push current in until it picks up, and if it picks up within plus or minus 3% of the setting, I'm going to call it good. That's how we're going to grade that. The other thing we need to look at is the time delay. So we do have an accuracy on the time delay, so it's plus minus 0.5% plus a quarter cycle. There's some oddities there, and we'll get into that once we actually start testing. So back in Protection Suite, we're going to hit this little down arrow to create a new test macro. Our macro that we're going to use is, well, let's think about this for a second. I have a bunch of different ways that I can do this, and I want to explain a couple of them so that you have an idea of how you would do this with your own software in case you're not using Protection Suite. Realistically, what I need to do is I need to inject 8 amps and I need to record if the pickup happens within that plus or minus 3% tolerance. So I've got a lot of flexibility here. I'm going to show you I would say the simplest test first. We're going to do a creep test. Protection Suite, they call it a manual current ramp creep I. So the creep I test, so this is going to be our manual, we'll call this 50P1P, 50P1, Jesus Christ. So we're going to call this our 50P1P manual test. This is our manual pickup. This is just one way to do it. And then I generally name them, because we have to do this test on all 3 phases, I'll write out the name like that, 50P1P manual test. And because in a previous episode we talked about bringing all of the protection settings into Protection Suite, into the software, I can use the setting name as a variable. So if I have to go to another relay, I can just plop in a new protection setting group, and the rest of my macros will populate with the new setting automatically, which is pretty cool, so I don't have to type that in a million times. We're going to do, this is just a phase current, right? We're going to do 1 phase at a time, and I'm not going to use a contact output. We're just going to talk straight to the relay, and we're going to ask the relay when it picks up, and we're going to record that manually. And this works great. We don't have to do anything crazy here. So we're going to say our expected value. I hit the the equal sign key to bring in the formula bar. And I'm going to tell it that my expected value is 50P1P. That is my phase overcurrent level 1 pickup. Great. Now here we can start from, it gives you this cute little graph on the screen. It tells you, hey, this is where we're going to start. So A is the amount of current that we're going to start with, and we're going to ramp until C, that is the amount of current that we're going to stop at. E is how long each individual, the minimum time each individual step is. We're going to ramp this manually, so it doesn't really matter. Delta current, that's how big each step is, how much current we're going to increase by. And then B is a amount of time that we start out at this offset current. So we can really save a bunch of time by not doing steps all the way up from 0. You could step all the way up from 0 if you wanted to. I know that my tolerance from the book we just talked about is plus or minus 3%. So if I start outside that band, again, I have to test to make sure that it's more accurate than the book says. So I have to start outside that tolerance band and then creep my way into it, expect it to trip somewhere inside the tolerance band. And then if that doesn't happen, keep ramping outside of that tolerance band. So what we can do is I can make the offset current setting, in this case, be my expected magnitude, 50P1P. We're going to start below, right? We'll say 5% below. So times 0.95. So we're 5% below my pickup amount. We're going to ramp upwards into the tolerance band, and then out of that, so my current limit, where do I want to stop the test? Well, we're going to do basically the same thing, 50P1P, just bigger, right? 50P1P times 1.05, so 5% higher. And then my delta current, so my step size, in this case, doesn't need to be super accurate. We're just going to make that 1% of the setting, 1% of the tolerance, means that each step it goes up by 1%, and then I have 6 steps that would be in tolerance and steps on either side that would be out of tolerance. It's a really easy way to do that. Sweet, and so we can manually ramp until we see that element pick up. The last thing that I need to do here this is specific to Protection Suite, we need to go to our test points. And it says our expected value here is 8 amps, which is my setting, which is great that it pulled that in. And then my tolerance from the book is it's a little bit wider than 3%, but we're gonna call it 3%. So this will give us our pass-fail criteria. If we get this to operate within tolerance, I get the green check mark. If it doesn't operate within tolerance, I get a little red X. Great, love that. So now I have to turn the test set on and connect to it. I've had it off the whole time because the test set is kind of loud. All right, so we're gonna start the test running, and then I'm gonna go to I'm gonna bring up the HMI so that we can see the targets that we're looking for actually pick up. In this case, we're looking for 50p1 to pick up. I showed in a previous video how to do this through the terminal window. If you're curious, or if your HMI is taking too long to update, that is also a possibility. So we're looking here for 50p1p. This is the instantaneous overcurrent element, number 1 pickup, right? Oh, I hate that about this. It brings that to the top. Okay, 50p1p. When this goes yellow, then we know we've picked up correct. There we go. It drops out right at, oh, it's like right on the verge. It's like flickering a little bit. I'm not sure if you guys are gonna be able to see that on the screen recorder. When I go up 1%, it stays in, and that looks really good to me. I'm totally happy with that. So we're gonna hit manual sense right when we know that it picks up. So 50p1p right now is high, it's yellow. So I'm gonna hit manual sense, and this is gonna record manually what we saw visually, right? And that looks good. And that's a totally usable, serviceable way to test this element. There's nothing wrong with the way that we just tested that. Great, love it. Is that how I do it? No, I'll show you a better way. We're gonna go insert a different macro. In this case, we're gonna do a linear ramp, which instead of me manually clicking up and down to make it pick up, I want the test set to do all of the heavy lifting. I can automate this, take the workload off of me, make it a less manual process. We're gonna do the same thing, and again, I have to do this on all 3 phases anyway, so we'll just do a different macro for each phase. We're gonna do a linear ramp current, LRampI. They call that macro LRampI. This will be our 50p1p, goddamn, 50p1p linear ramp. And this will be our test for B phase. So similar to before, we're gonna do the same thing. Our test points, our expected value is 50p1p, which is the same variable as before. Our tolerances are the same as before, plus minus 3%. And we're gonna make our action value on B. So B phase is gonna be the only current that's getting output, right? Remember from here that this is, so 50p1t is part of the trip equation for our trip variable, which goes to output 101. So I've got a input on my test set wired to output 101 on here. It's a dry contact on the relay, so whenever the output on the relay closes, the test set can sense that, and then it'll stop the test, which is here. So our sense connection is open to close. If you had something that was like a dropout, you could do close to open. If there's a failsafe output on your relay, close to open works really well too. In this case, we're doing open. And then LN1 is the logic input 1 on the test set. That's just what it's named. So same as before, you'll notice that so our manual test looks very similar to our linear ramp test, except the test set's gonna do it automatically, and it's gonna stop automatically when the contact closes. We need to tell it to start basically the same way. So we're gonna tell it 50p1p is our pickup value, and I wanna start 5% below that, so times 0.95, 95% of our setting. Now I do, in this case, need to give it durations because it ramps automatically. I don't want it to just start at 1 and go to 1,000 in one step, so I have to give it a time delay on each step. And you know, I have my protection suite set up in cycles, so I do 15 cycles. If you had yours in seconds, you do a quarter second. However you want to do it, doesn't really matter. Our offset duration, I generally make that the same as our delta time. So in this case, that'll be 15 cycles as well, which again is a quarter second. Delta current, same as before, 50 P1P, which is our setting that we're trying to test, times 0.01, so 1% steps. That works totally fine because I'll have 3 steps on either side of the setting that are within tolerance. And then our current limit, again, we're gonna make this go 50 P1P times 1.05. So just as before, we start 5% low, end 5% high, and then I've got my tolerance band in between that. So I think we're all set up. I've got the test set hooked up. When output 101 closes, this will record the amount of current that the test set was putting out when it saw the contact close. Hit pause and go down in the comments if you know why this isn't going to work, but I'm gonna run it anyway just for posterity. Interesting, I got a sense check error from my test set. This shows up in a bunch of different ways on different test sets, on different software, but what that means here is that the contact state for output 101, it was expecting it to be open, it was expecting it to be open and then close during the test. This was closed, out 101 was closed before starting our actual ramp test. Now, I can tell you what it was just from experience, but if we go here, we'll pull up our terminal window, oopsie, turn that off. Pull up our terminal window, and I ask for the last 10 things in the event recorder. Whoa, look at that. It said the last element that picked up was, well, the last element that picked up was 50 G1P. That is our ground overcurrent, which is another element. So that's not what we're testing. Something that we aren't testing triggered the trip equation and triggered out 101 to close. So now I've got a couple different options. I can either just stick with the manual test and look at the pickup like we did before, or I can send 50 P1 to an isolated output and test it on a separate output. And that's a pretty easy thing to do. We talked about how to change individual settings in a previous video, so I'm not gonna go into length about that, but we're gonna go to AC, hit caps lock, do our level 2 password, and I'm gonna go set out 101. I typed that in wrong. We're gonna go set L out 101 terse. Goes a little bit quicker if I do that. Instead of out 101 closing when the whole trip equation goes high, I want it to be the individual output that we're testing. So we're gonna tell that to go output 101 should equal 50 P1T. And then I type end, hit yes to save it. It updates very quickly. There we go. And now we're gonna run this test again. So this is our linear ramp. Boom, there we go. And we can see that it ramped the current up to 8 amps. And at some point along that, 50 P1T triggered out 101 to close, and we recorded the current tolerance, the accuracy with which that pickup happened, and it was less than our step size, or we're right there at 8 amps. Looking perfect. I got a 0% error on that test. So it looks good. If we go to our results tab, hey, we failed this first test, and the second test, we did it better the second time, we just didn't screw it up, so it passed. Again, operator error is more likely to happen than an issue with a 751 relay. They do happen, and that's why we test them. But there is one other macro that we can use for, well, there's actually 2 other macros, and they work pretty similar. There's one called pulse ramp I, P ramp I, pulsed linear ramp, which works very, very similar to the linear ramp, except it has an offset current. It offsets between pulses. So it goes in distinct pulses, and the pulses go up, they ramp up over time. That's a pretty useful one sometimes. I use this one a lot. If your overcurrent element has a really large magnitude, it's like 30, 40 amps, something like that. I don't necessarily want to heat up all of the components and the test leads and I don't want to overheat my current output cards on my 6150, I generally will use this pulsed linear ramp instead of the linear ramp if we're doing very high current outputs or there's like a long delay and I want to hit a discrete amount of time on each pulse. Pulse linear ramp works really well, and this is generally what I would use for this test. If I'm doing the pickup on an instantaneous phase overcurrent element, I would generally use the pulse linear ramp. There is yet another one that also works. It's called binary search I. So I do want to say honorable mention to the binary search current. This one works really similar to the pulse linear ramp, except it does a pulse that's like way below tolerance, a pulse that's way above tolerance, and then like shrinks into the tolerance band so that it can run faster. Basically the same benefit as we talked about before on the pulse linear ramp macro. This one I think is sort of the best choice for electromechanical relays where you'll have an overcurrent element that's just a solenoid basically. This is a really good way to test those. It tends to be faster, components don't heat up quite as much. In general, I will prefer for testing a microprocessor based relay, my preferred macro for 50P1P is going to be the pulsed ramp, P-ramp I, pulse linear ramp current. And I will show you how to set that one up here as well. So this is pulsed ramp, and we're gonna do this one on C phase. So again, same setup as before. We hit the equal sign to punch in a formula. So 50P1P is my expected value. Offset current, again, 90%. Times 0.5, that's fine. So I will give this a 15-second offset duration. Our initial current, so this is a new variable that we didn't have on the linear ramp. Our initial current is the first pulse up. So I will actually make this one that 95% amount, and then I can have my offset current be 1 amp or even 0 amps. So we pulse on 95%, and then we pulse off, and then we pulse on 96%, and then we pulse off. That's basically what I want. And then between each tests, we just have, oops, that wasn't it. Between each test, we have a 15 cycle or a quarter-second delay at 0 amps. And I tend to use this one just because it heats up the components less than doing a linear ramp. It allows the components to cool down and not be on as long for a big long ramp. So our current limit in this case, again, I want that to be 50P1P times an extra 5%. Your delta current, we're going to do this again at 50P1P times 1%, 0.01. Cool, so this is all basically the same. One thing I would say on this duration, well, we'll get to that in a second when we do the other one. We're going to do C phase. That's our action, that looks good. And run test, and this should work. Oops, I didn't put in a tolerance, my bad. Put in our plus minus 3% tolerance. We're going to run the test. This will run a little bit slower than the linear ramp just because we have, every time it takes a step, it also waits at 0 amps. But realistically, it's not that big of a deal. It's not that much more of a time delay. Cool. So that is an instantaneous overcurrent element with no delay. That's all I have to do. I need to determine the pickup, whatever method I decide I want to do that on as a technician, whatever works best for me, whatever fits my workflow, whatever's easiest or most logical. Any one of those tests, the manual test where we look at the light, the pulse test, a linear test where we get a contact close out of it, any of those will work just fine. I don't need to test the delay if the delay is set to 0 seconds because there is no intentional delay. We know that it goes really fast. I'm going to do the same thing in this example with 50P2T. We'll go insert a copy, grab whichever one you want to copy, and we hit the down arrow on that, and we go insert a copy of selected test, and then I don't want the results because I'm doing a different thing here. We're going to change it around a little bit. This is going to be 50P2 pulsed ramp. We're gonna do that on A phase. That looks really good. Make sure all that's checked. So because this is a formula, I can just click here and change that formula to bring in the other element that we're looking for. So that will come up at 0.6 amp, or 6 amps, right? So let's go ahead and run this. I think I called this A. Yeah, we call that A. So we're gonna do this one on, this is gonna be our pickup on A phase, right? And we'll see here, these are calling in for the wrong formula. So we'll just tweak that to be the correct formula. And if I run this, it's the output that we're reading is still 50P1T. So I need to change my output to 50P2T. So element 2 is what operates this. So we're gonna set L out 101 terse. I'm gonna change this to 50P2T, right? And are you sure? Yes. Whenever this pops up, we'll hit go. And pause now and tell me in the comments why this isn't going to work. We're gonna run test. Seems like it should work, right? We changed the element that triggers that output. Should work great. No op, it didn't operate. Why didn't it operate? Well, because our pulse duration is 15 cycles and 50P2T triggers after 1 second. So it's 60 cycles. We didn't pulse it on long enough to get this to trigger. I again have multiple options for how we're gonna fix this. Number one, the easiest one, I can just set this pulse duration to be longer than the delay of that pickup. So that's one way that we can do that, and I'll show you the next one on the next one. So we're gonna change this formula to operate in seconds, and then my delay setting for instantaneous overcurrent element 2 delay is 50P2D in seconds. And I never want to do it at like exactly the right amount of time, so we're gonna, plus a quarter second or something like that. So it's gonna go longer than that duration, so that each step is longer than the delay. We're not testing the delay. Remember, we're testing the pickup. I need to determine the pickup magnitude of this instantaneous overcurrent element. We will test the delay later, and I'll show you how to do that. So we're gonna see this, and it is worth noting that test macro took a lot longer to run because we have long pulses each time. It's worth noting, it's just something to keep in mind. If you had a test that was, or had an element that was, maybe took 60 seconds to pick up, under voltage and over voltage elements sometimes will have really, really long delays on them. It's something to keep in mind. Is there a faster way to test that? Okay, well, let's grab the same macro that we had before. We're gonna append a copy, no results. Append just means put it down to the bottom. Insert means put it directly underneath the previous one. So we're gonna say this is 50P2 pulsed ramp B. We're gonna do this with no delay. We're gonna test this one a little bit different. So this one has a different name on it. Okay, similar setup. Again, we're gonna change all our settings. This is 50P2P. This is 50P2P. And notice I'm not gonna change the pulse duration here. We're gonna test the relay in a slightly different way. What I'm gonna do without changing my pulse duration is I'm gonna tell the relay to close output 101 whenever I see the pickup. This will work absolutely phenomenally. So we're gonna go set L out 101 terse. In some cases, this is the preferred way because I won't have to wait for a long delay every time I do this pulse. So we're gonna set L out 101 terse. Instead of 50P2T, which is the timed output, we're just gonna do 50P2. I think 50P2, not a valid element. Okay, so we're gonna call this 50P2P. Yep. So whenever 50P2P is picked up, output 101 will close. Beautiful, worked great. Basically the same results we got last time. C phase, What do you think? What do you think? Should we do a different thing on C phase? Let's do a different thing on C phase. Let me show you the binary search. So this will be a different macro. So this will be our binary search binary search current I. So this is going to be our 50p2p binary search. And this will be our C phase test. Again, we have to determine this pickup, the instantaneous phase overcurrent pickup on all of these. Our expected amount is 50p2p, which is 6 amps. Great. Our offset current, in this case, we're going to leave that at 0. Doesn't really matter. Offset duration, 15 cycles. Current limit, this will be 50p2p times 105, so 5% high. Sounds good. Pulse duration, we can do this at 15 cycles. Again, the output is being triggered off of the pickup value, not necessarily the trip the trip word bit. It's going off of the pickup value. So our weight, we can also do 15 cycles. Our delta current, in this case, we're going to do the same thing. This will be 50p2p times 1%. Then our delta time, we can honestly do that one a little bit faster, doesn't really matter. And then the rest of this is going to be set up exactly the same way. Same tolerance, plus minus 3%. And I don't use this one very often on SEL relays, so I'm not 100% sure how the relay is going to react, but I think it should be pretty similar. There you go. Bingo. Works exactly the same way. It just does it a little bit quicker than the pulse ramp because it doesn't step way outside and then step way inside. It works a little bit faster. I don't know. Is it worth the extra headache to set up? Not really. Okay, so currently, and I'll go ahead and start highlighting these things as we get them done. So 50p1t, we did that pickup and there's no delay, so I don't necessarily have to test it. 50p2t, I tested the pickup on all 3 phases, so that I'm good with. I'm happy with the fact that the setting is 6% and we know that it operates within plus minus 3% of those 6 amps that it needs to pick up at. How do I determine that 50p2t has this time delay? Also, what accuracy is that? So our accuracy for this time delay is plus minus 0.5%. We might need to talk about that, but we'll get set up here. There's really one macro that there's only one macro that you can use to test this time delay that I would use. There's probably a couple others, but we're gonna use, and I would recommend you use in this instance, the operating time current, so time I. Oops, I put that in the wrong spot. So we're gonna do time I, so this is gonna be our 50p2t. Now it doesn't necessarily matter which phase we did this on. I do check the pickups on all 3 phases. I don't necessarily need to do the time delay on all 3 phases. I'm happy with it being 3 phases of pickup and 1 phase of timing because it's more of a logic test than anything else. Now our expected value, remember we had this setting that was already pulled in. This is setting 50p2d is our delay, and that of course I have to tell Accelerator, or I have to tell Protection Suite that that's in seconds and not cycles. So 1, the variable that pulls in is 1 because my delay is 1 second in Accelerator. Protection Suite, I have to tell it that it's in seconds. So 60 cycles there. Our action, we'll just do on A phase, doesn't really matter. Our offset current. Now I could do this at basically any current below my pickup value. So it could be 0, it could be 1, it could be 3. Generally what I'll do is I'll do like half of my pickup amount. That should be fine. Offset duration in this case, we just want to give it enough, be out of the tolerance band for our test so that if it picks up at the wrong amount or picks up the wrong time, we can get a failing test. It helps us get a failing test if we've got some amount of offset duration so that when we clock the actual time starting, we know that the test, the thing that we're intentionally doing is starting the clock in the relay, right? So I give it an offset duration of 15 cycles, any amount. You could set this to a minute, you could set it to 0.1 seconds, whatever you want, that doesn't really matter. Our test current now needs to be above the pickup that we're trying to hit. So this is 50 P2P outside the tolerance band. Remember, our tolerance band was plus minus 3%. We'll do this at plus 0.5. So we're going to be above our pickup outside the tolerance band. We're not testing the pickup anymore. We're testing only the time delay. So 50 P2P times 1.05 is 5% high. That looks good. And our max on time, I usually make this a formula in Protection Suite. We'll do 50 P2D, which is our delay. Again, make sure it's in cycles. Plus some amount more than my tolerance band, which is plus minus 5%. We'll just say it's our expected delay plus a whole second. It's really not going to take that long for this test. Our tolerance here per the book is 0.5%. So we're going to go plus minus 0.5%. We're going to run this, and it might pass. We'll talk about it if it doesn't. It will certainly come up. The issue that I'm expecting will certainly come up in this episode. Ah, yes, I did not change the operate logic on the output, so we're going to go set L out 101. We're going to set this to 50p to T, which is our timed element output, not the pickup. We can see on the relay, I don't know if you're looking that close, but the trip light and the instantaneous light come up on here, which is cool. Now we're doing the timing test because I have the relay programmed correctly. All right, so we see here that this tripped 2 cycles after, or what we actually measured was the test set recording the output contact here closing 2 cycles after we expected it. This is a very, very common thing that happens in Protection Suite, especially with the 6150. There is a hardware built-in debounce timer for the inputs on this. So I, as the technician, need to be aware that there is an inherent time delay in my test set. There is an inherent time delay with my test set reading the inputs. That is a thing. You have to come to terms with it. It is a little bit complicated. So if the tolerance, if the delay, the input delay of that is longer than the tolerance of the test that I'm running, the time delay that I'm trying to record, I need to set my test plan up accordingly. I need to set my test plan up to allow for the input delay of my test set. Generally what that means is on time delay tests that I'm doing, I will change this from a percent to an absolute, and I will say my tolerance is minus 1 cycle and plus 3 cycles. And you're saying, well, wow, that's way less accurate than the accuracy that we have to test the relay to. Yes, I'm aware of that. This is the reality. You're testing with imperfect hardware in an imperfect world. We're just going to, we're gonna call it good. I know that I have this inherent plus 2.5-ish cycle time delay as part of my test set that I have to add on to my expected delay value. So I still have a little bit of tolerance on that. Basically all of the time delay things that I measure that are less than a couple seconds, I need to use an absolute tolerance of minus 1 cycle plus 3 cycles. It's universal for the 6150. It will probably be different on your test set if you're using something that's not a 6150. So we're gonna run this again, and I know it's gonna pass because we saw the thing actually operated, it recorded it operating at 62 cycles, which is intolerance. Intolerance now. Cool, so love that. Okay, so we have now done 50p1t and 50p2t. And I think that makes quite a bit of sense. Our next test here is gonna be 50n1t, which is a neutral. And this is gonna work almost identically to our 50p, except 50n is a separate channel. So how do we get current on that channel? Well, we're gonna grab one of these, we're gonna hit append, yes, and I'm gonna change this to 50n1p, it's just a pickup, so that should be fine. Cool, I'm gonna change my variable name to 50n1p, that's my pickup amount, and we can see over here, this is the setting that we had. And this is why I have the settings cheat sheet, so I don't actually have to remember all of this stuff. Our pulse duration, in this case, we can just set this to 50n1d plus 0.25 seconds. That's plenty of delay. Got to make sure we do these. 50n1p times 95%. Delta current, 1% of my 50n1p. And then my current limit is 50n1p times 105%. So all of that looks good. Our test points, our tolerance is still set correctly. Sources, I need this to be the IN current channel on my relay, which I currently have wired up to the terminal here. If you're looking at the top of the relay, this red terminal in the bottom right corner, that's my IN channel. And I just set this IN channel to action. So I just added a source in my sources tab for that specific channel, and that's already wired up. For me, that's already wired up. If you're doing this in the field, you would have to wire this additional source into the IN channel on the relay. All that looks hunky-dory. Cool. So we're gonna save that, and we're gonna run it. Oh, did I change the thing already? I don't think I did. So we're gonna stop. We're gonna set L out, 101 terse, 250 and 1T. And save, yep. Wait for that to come up. Okay, so my enable light came back on. It blinked at me and said that it's good, so it took the new settings. Sick, that worked awesome. And we'll do the same thing. We'll take 50p2t and we'll just whack a copy of that down on the bottom. So this will be 50n1t. Change a few settings around. 50n1d is my expected delay time. Again, my tolerance is going to be the same because it's not based on the tolerance from the book or the setting. It's based on the debounce timer, the input debounce of my relay test set. Just a fact of life. Again, we got to go to the sources tab, add channel IN because we copied this from one where we hadn't added that source already. Put in the new action, get rid of the old one, so that all goes back to that. 50n1d is my expected time delay. We're going to change all these settings. 50n1p is my setting my magnitude that we're working around, my pickup value that we're working around. All right, we should be able to run that and clock the time delay there as well. Cool, sick, love that. Got a good result. Again, we'll see it was almost exactly 2 cycles slow, which is what we saw on our phase time over current. It's almost exactly 2 cycles slow. That is the delay of our relay test set. Okay, cool. So I got those two. Up next is 50G1T. This is the one that tripped on us last time when we were doing our 50P1P pickup, because this is a calculated 0 sequence current. And I'm going to show there's 2 different ways that we can do this. We can either, we're going to do, what macro do you guys want to use? We'll do a linear ramp. I think it'll cut out as much of the confusion as possible. So we're going to go L ramp I, and we're going to call this 50G1T, sorry, 50G1P single phase. There's a couple different ways that we can do this because there's a lot of different ways to get calculated ground fault current to come in, right? So this will be 50 set L out 101 terse 50G1T. Cool. Take a second to kick in there. Again, we hit equal sign type in our expected pickup values. This is going to be 50 G1P, my pickup magnitude. My offset current, where do I want to start ramping from? Similar as before, 50 G1P times 0.95, so 5% below our expected value. Offset duration, 15 cycles, doesn't really matter. Delta time, in this case, I have no delay on my 50 G1T. We're just going to do the magnitude pickup. I don't have a delay here, there's no delay. So my delta time, 15 cycles, is more than enough. My current limit, 50 G1P times 1.05, so 5% high. And then our delta current, again, we'll do 1% steps because it makes life easy. 50 G1P times 0.01. So that's our ramp amount. We ramp by 0.5% every time. So with this setup, the way that we have it, our out 101, our output contact is programmed to close when 50 G1T picks up. Basically, all I need to do is put current on a single phase, because 100% of the current, if all of it is in one phase, is zero sequence current. It is going to be read as ground fault current. If you only have current on one phase, that's what it's going to look like. So I should be able to just, again, I hit save religiously. Oopsie doodles. I always do that. Got to put in my tolerance. We're going to run that. I need more Diet Dr. Pepper. Sweet. We got instantaneous. Ground neutral 50 trip is what we say here. That tripped a little bit low. That's actually kind of interesting. Why did it go so low? 0.9 amps. Do that again. Why are we tripping below the tolerance? That is interesting. Da, 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 da. Accuracy, plus minus 3% of that, plus minus 0.02% of I-nom. So perhaps we are still within tolerance, but I need to adjust my tolerance calculation. Let's try it. Let's see if that's the fix for this. So it's plus minus 3%. See, zoom in so you guys can read this. Plus minus 3% of the setting, plus minus 0.02% times I-nom. In this case, I-nom, our nominal current for this relay, is 5 amps on the secondary. Maybe that's it. So let's walk through the process of making a custom tolerance. What I generally do if I'm doing a custom tolerance for one macro, for one test or one element. My apologies, the camera battery died. So we have to make a new tolerance for this to be a little bit wider, to be a little bit further out of the tolerance band here. So this is basically this formula out of the manual. So they're asking for, come on. The manual says it's 2% of the nominal and 3% of the setting. And so on the low end, we have to subtract that amount difference. We have to subtract that from our expected value. And on the high end, we have to add that to we have to add both of those things. So it's plus plus and then minus minus for both ends of the tolerance. I feel like I'm not saying this right, but we can see that the values, the absolute values here are higher and lower than we expect. So then we're gonna go back to our test plan here, and I'll change this to min max, and our max is equal sign so that it knows it's a formula, and we're pulling in a variable. An equal sign here, and we'll tell it that is a variable as well. And we should be able to run that again and see what we get. Hopefully it is within tolerance this time. Nice, beautiful. That was perfectly within tolerance. Looks great. We can save that and call it a day. And we know that that element, even though it's a little bit outside one of these tolerances, it's within the labeled tolerance for the element. So everything is good there, totally happy. And again, I was testing this wrong. I was testing this to the wrong amount of tolerance. So we'll get rid of all that crap. Cool, great. That is one way to test 50G. What is the other way to test 50G? Well, glad you asked. We can do the same thing, basically. And we're gonna say 50G1, three-phase. Three-phase. So zero sequence current is all of the currents in a line. Basically what we're trying to measure with a zero sequence CT or the calculated zero sequence amount is current leaving the system. It is no longer balanced. It is going to ground. It is leaving the power system. So what we're gonna do is this is the first time that we've had to pay attention to phase angles. My normal happy phase angles would be 0, 240, and 120, A, B, and C, right? That's a balanced normal three-phase system. In this case, I'm gonna make sure I leave A, B, and C phase currents in phase. They are all at 0 degrees. So we still have 100% of 100% of the current in the system is going to be zero sequence current. And now what I do is I say action times a factor, and that factor is going to be, we're gonna divide it in 3. We're gonna divide all three phase currents by 3. As much as we can, 0.33333. And then we should be able to run this and get the same result, but I'm measuring it by doing 3 phases of zero sequence current instead of 1 phase of current on an unbalanced load, right? And look at that, and we got the same exact result as we did before. That's great, that's totally what I expected. Wink, wink, totally didn't expect that to work. Just kidding, I knew it was gonna work. All right, so we go back here. There was no delay on that, so I don't need to test that delay. Now, negative sequence, 50Q1T. I believe if you look at the SEL manual, it will tell you a specific way to test this. I'm not sure if it's for the 751, it might be the 351, might be a different relay. I don't know, I might be misremembering this and making it up completely. The way that I test this is different than the way that I remember SEL training people on how to test this because I like my way more. What we're gonna do is let's just make a new macro, pulse ramp. Generally I like pulse ramp for basically everything. We're gonna do a pulse ramp current, insert steady state test, P ramp I, pulse ramp I, and this is going to be our 50Q1, Jesus Christ, 50Q1P. Anytime you see negative sequence current, I want you to think it's rotating the wrong way. If I'm expecting ABC rotation current, this negative sequence current, it can be calculated a lot of different ways. It can come about a lot of different ways, but the way that we're going to test it is by applying negative rotation, backwards rotation. So in this case, I need to do both a pickup and a rotation check. I need to do a sequence check. So those are two different things. If we look at the NIDA ATS for a negative sequence current pickup, I don't think it's gonna tell us anything in particular. I haven't actually done this ahead of time. Negative sequence current relay, determine negative sequence alarm level, determine negative sequence minimum trip level. So I don't have an alarm in this case. I just have the trip. Maximum time delay, and 2 points on the I2T curve. Okay, well I don't have a lot of these, right? I have a time delay, and I have a trip level. I am lazy. I wanna make sure that it works. I need to be able to argue definitively that the way that I tested it proved the element works correctly, and I need to do it quickly and easily because I'm a lazy piece of shit. All right, so our negative sequence overcurrent pickup. Like I said, we haven't talked too much about our phase sequencing. Normally in an ABC rotation system, which is probably going to be 90+% of systems that we work on, unless you live in a very specific region where your utility has backwards rotation. Don't worry about that unless you're that guy and you have to worry about that. I can't help you too much. Normally on an ABC system, we're going to inject currents positive sequence. So 0, 240, 120 counterclockwise leading angles. Engineering speak for when we inject current and we don't want to intentionally have a negative sequence thing happen. We want positive sequence, normal forward rotation. I want to inject 0 on A phase, 240 degrees on B phase, and 120 degrees on C phase. And that'll give us the correct forward rotation for 99% of our applications. Now, when I'm doing a negative sequence over current element, I basically want to do that backwards. So we're going to grab this one because this one has our custom tolerance the way that it was before. So we're going to grab that and we're going to hit append copy. Don't copy. We can do this one. Doesn't really matter. Don't copy results because it's basically the same test except we're just doing a wonky thing with the phase angles. So this is going to be our 50Q1P, and we'll call this our magnitude pickup because I need to verify that it works both on the magnitude and the phase angle change. 50Q1P magnitude, we'll call that good. Okay, so we're going to change these settings, 50Q1, and this, I need to change all of the G's to Q's. This is going to be a little bit different. It does change my overall tolerance. That looks all good. And now, instead of this being 0 sequence, I want it to be negative sequence. So here I'm going to do 0, 120, 240. So I'm rotating counterclockwise or clockwise instead of counterclockwise. All this should be fairly similar. Going to be happy with that. Our delta time, in this case, we're going to change that to be 50Q1P, or sorry, 50Q1D plus half a second, and my delays are in seconds, so I got to make sure that is lined up. Okay, 50Q1P times 105%. So that, I think, all looks good. I did go ahead and change, this might have been when my battery was dead. I did change my output 101 to 50Q1T, so I'm on the right output. And look at that, it worked beautifully. I love that so much. So we got this to pick up by starting in negative sequence and ramping just the current up until that magnitude increased. What I would like to do on our next test, because we have to do the timing anyway, I have to verify this timing. What I would like to do is verify that the sequence itself, the actual phase sequence, is what causes this to trip as well. And fortunately, I can combine that in with our time test. So we're just going to do a time I, just as we did before, operating time current. All right, so this will be our 50Q1T phase reversal. So we're checking two things here. We're checking that the time delay works correctly. We get that 0.5 second time delay dead nuts accurate. This one is going to be dead nuts accurate. And then we're also going to verify that the phase sequence itself does actually cause this and not just any amount of current over 1 amp, right? We're going to do our best here to make this make sense. 50Q, I have to hit equal sign, 50Q1D in this case is going to be 0.5, so we'll turn that in seconds. There we go, 30 cycles, half a second, 30 cycles, whatever. Offset current. What I really want to do is have this be way more than this negative sequence magnitude, just in positive sequence. So we can do that. That's a thing that we can do. Actually, I think I have the wrong macro. I'm not looking for a current response, I'm looking for a phase response. So we're going to do a phase response test, which would be time phase, single point with a timer. Boom, that should be good. 50Q1D is our expected time delay that we're trying to hit. The current that we're going to run here, we're going to do 2 amps on all these. And then this is going to be my action. Does this work? That one's going to be 0. That one's going to be 240, and then this one is going to go from 120 to offset is going to be 120. Pulse duration, we're going to do 60 seconds, just give it a nice long lead up to it. Our test phase in this case is going to be also 240. That should give us enough negative sequence current to trigger this negative sequence overcurrent amount, right? Our max on time, we're going to say, is 50Q1D plus half a second. And that should get us in the ballpark of working. Test points, again, we're going to do absolute -1 cycle plus 3 cycles because we're expecting a 2-cycle debounce timer delay. And we hit that, and we'll see what we get. This is a good example of one test proving multiple things. Like I said, there we go. Everything is Gucci. All right, guys, so that was every 50 element, every instantaneous overcurrent element available in this SEL751. We did the phase overcurrent, the neutral, the ground, and the negative sequence instantaneous overcurrent elements. I showed you how to do them with delays, without delays. A couple different permutations, a couple different ways to do each of those things, and you get to pick which one works best for your situation or your flavor of relay testing that you prefer. Hopefully you found this video helpful. Definitely do all of the YouTube stuff, like, share, subscribe, comment down below. It really does genuinely help me out, and if you want to help out a little bit more, consider hitting the join button down below and supporting me for as little as $2 a month. I definitely appreciate it. It does encourage me to make more of these videos. They take a really fucking long time to put together, so I certainly appreciate your support. Check out the other videos in the SEL751 Masterclass. The course should be linked somewhere here on screen. And yeah, stay safe. I'll see you in the next one. Thanks, guys.